Somewhere on this counter is a loaf of bread, and somewhere smudged, water-stained, unreadable is the recipe that made it. The flour, the water, the warmth, the time. Here's the question that hides underneath every model we fit. If all you're handed is the bread, can you read the recipe back out of it? Not always. And the reason why turns out to be one of the most useful things a single number can tell you. Start with one knob. Nudge the hydration, and the crumb changes. You can watch it open up. Nudge the feeding schedule by the same amount, and nothing. The bread comes out the same. That difference, how much the loaf moves when you turn a knob, is exactly what a model means by information. The more a parameter shows up in the data, the more the data can say about it. Stack that up across every knob and every pair of knobs, and you get the Fisher information matrix I of theta, a grid of how loudly each setting speaks in the bread. Here, the bread picture has to step aside for the precise statement. That matrix is the curvature of the log likelihood, the sharpness of the peak, in the function that scores how well a recipe explains the loaf, measured at the true recipe. A sharp peak is a knob the data pins down. A flat one is a knob it can't. So lay them all out. Flour ratio, hydration, fermentation temperature, feeding schedule, 4 knobs. Call them theta, the recipe written as numbers. You only ever get to turn them. You never get to read them. The one thing that comes back is the loaf, and everything from here is working backwards, from the bread to the dial settings, using nothing but how much each dial left its mark. Here's the twist that changes everything. The bread doesn't taste your ingredients one at a time, it tastes combinations. Turn up the flour and the water together, and you've changed how wet the dough is, and the bread notices immediately. But other combinations, it's almost blind to. So the directions that matter aren't flour, water, temperature, the things you wrote on the card. They are the combinations the bread actually tells apart. Wetness, fermentation extent, and they sit at an angle to your original knobs. That rotation has a name. You take the information matrix and break it into its natural directions, its eigenvectors, each carrying one number. Its eigenvalue. I equals Q lambda Q transpose. Q holds the directions, lambda holds how sharply the bread pins each one down. A large eigenvalue is a stiff direction, the data sees it clearly. A small one is a sloppy direction, the data barely feels it at all. Watch what that sloppiness actually does. Here are 2 different recipes, genuinely different. More flour here, less time there, a warmer proves. And here are the 2 loaves they bake. They are the same. Crumb for crumb, crust for crust, the same bread. Each recipe sits at a different point along one of those sloppy directions, and the loaf simply cannot tell them apart. This isn't measurement noise you can average away. The information to separate them was never in the bread to begin with. This is the moment every modeler has lived through. You run the fit. The optimizer reports that it converged, and the numbers it hands back are nonsense. Here's why. Along a stiff direction, the score for how well a recipe fits has a real peak. Turn the knob the wrong way, and the fit gets visibly worse. So the optimizer is pulled back toward the top. But along a sloppy direction, there is no peak. There's a long, flat valley. Drop the optimizer in from one starting point, and it slides to here. Drop it in from another, and it slides to there and settles, just as happily, somewhere completely different. Same loaf, same score, a different recipe. It didn't find the answer. It found wherever it happened to start. How flat that valley is comes down to one number, the condition number, the largest eigenvalue, divided by the smallest. For these models, it can run past 1,000,000, which means some combinations are 1,000,000 times harder to pin down than others. And your uncertainty follows the same law in every direction. The wobble in an estimate grows like one divided by the square root of its eigenvalue. Big eigenvalue, tight estimate, tiny eigenvalue, and the estimate smears out along the entire length of the valley. So the honest answer the data gives back was never a single point. It's this, the whole cloud of recipes that bake the same bread. That cloud is the thing you are actually estimating. Reporting one recipe from inside, it is just reporting where you started. And if you have ever fit one of these models, a population PK model, a transgenic colony breeding model, and watched a dozen runs converge to a dozen different parameter sets, every one of them fitting the data just fine, this is what you were looking at. Not a bug, not a bad optimizer, a flat valley, and 12 marbles resting wherever they rolled to. Now line all the eigenvalues up, largest to smallest. They don't cluster. They cascade, falling away across orders of magnitude, each one a fraction of the last. A few stiff directions at the top that the data sees sharply, and a long tail of sloppy ones at the bottom that it essentially can't. Biological models do this almost universally. The behavior even has a name: sloppiness. And here is the headline, the one thing to carry out of this whole video. A direction at the bottom of that tail is flat before you fit anything. No clever optimizer reaches it. No fancier algorithm reaches it. More loaves from the same recipe, baked the same way, do not reach it. There is a hard floor on how well any method can do the cramer-rao bound. It says the covariance of any honest estimate, how much it is allowed to wobble, is at least the inverse of the information matrix. Where the information is tiny, the wobble is enormous, and that is the end of the conversation. Which sounds like bad news. It is actually the most useful thing on the screen, because those bottom directions are telling you precisely which knobs to stop fighting over. Fix them, merge them, you lose nothing the data could ever have told you. But the data can't tell was always about this data, this loaf, this bake. What if you could bake again, hotter or longer, or at a different hydration, a condition where the combination that used to vanish finally leaves a mark? That changes the whole picture, because now the flat direction isn't a wall. It's a question you can go and answer. You have two honest moves. The first one is free. Stop insisting on the knobs you wrote down and rotate your coordinates into the directions the bread actually distinguishes. Fit the ratio of clearance to volume, and volume by itself, instead of clearance and volume separately. Same model, but now each quantity you estimate stands on its own. That's reparameterization, working in the data's natural axes instead of fighting them. The second move spends an experiment. You design the next bake to go straight at the blurriest direction. Push to make the smallest eigenvalue as large as you can. That's optimal design, sharpening the worst axis, or shrink the entire cloud at once by maximizing the product of all the eigenvalues, the determinant of the information matrix. That's optimal. Either way, you are doing exactly what the eigenvalues told you to do. Spend your effort where the data is blind, not where it can already see. So here is the whole room, on one wall. Every direction through your recipe, laid out by how loudly it speaks in the bread. The stiff ones at the top, the data simply hands these to you. The sloppy ones at the bottom, the data shrugs, and you either fix them or bake again to chase them down. The eigenvalues sorted them. The eigenvectors named them. And underneath all of it sits one idea. The loaf was never going to give you the recipe. It was only ever going to give you the combinations. It bakes differently. The recipe card never does get less smudged. But once you know which combinations the bread can speak, you stop asking it for the ones it can't, and you know exactly which question to go and bake next. That is what the Fisher information eigenvalues are really for. Not a diagnostic you run after the fitting is done. A map, drawn before you ever fit, of what your data was always going to be able to say.